All right, for those of you who are not with us today, I've just started the recording and today we are going over topic 40, Introduction to Neural Networks. And let me share my screen. Cool. So neural networks is 3 topics and one of the project topics will cover neural networks. Now, you can use neural networks for any kind of input data, but for the project specifically, you'll be doing on image data. So today, I unfortunately won't really go into image data, and that stuff will come probably in the next couple of study groups. But for today, we'll just talk about the basics of neural networks, how they work, and we're actually going to run a couple neural networks ourselves as well. So I've linked this notebook. By the way, I linked my entire study group repo for a cohort that's just wrapped up phase 4 as well. So feel free to peruse any of the notebooks if you'd like to see additional material. Really quickly, I've linked a Google Colab notebook. I don't know if y'all have seen Google Colab yet at this point. No? Okay. So Google Colab is basically a Jupyter notebook built by Google and it's completely run online. So because sometimes if your computer is not very strong, neural networks can cause the kernel to crash. It can be too much for the kernel. So I'm going to show you all Google Colab in the later half of this, just so if for whatever reason, neural networks aren't working on your local machine, you can actually port everything over to Google Colab. And you can actually use their like online GPUs, TPUs, whatever you need. So that's actually a really neat tool to go with. All right, in terms of this session, it's obviously being recorded, but also if you have any questions at any point, I actually like to be interrupted. So at any point, if anything's not clear, just let me know. All right, but in the introduction to neural networks, I'm going to actually show you all this in a little bit. But what we're going to hit today is what a perceptron is. So perceptron, think of that as a building block for a neural network. So we're going to talk about what a basic perceptron looks like and how that scales into a giant neural network. We're going to talk about multi-layer perceptrons, which is basically our neural networks, back propagation, which is how a neural network learns. And then we're going to talk about building our first neural network. We're going to implement one with Keras, which is the library that, that we use for neural networks on Google Colab. All right. So first to start, this article I like because of this cheat sheet, which is kind of wild because all of these are examples of neural networks. So some of the ones that we're going to hit in this course, we're going to talk about perceptrons. These are the most simple ones. You can see it's just like 3 nodes. We're going to talk about what these refer to later on. We're going to talk about feed-forward networks, deep feed-forward networks. We're actually going to see that by the end of today. Other ones that we're going to hit, if we go down this graphic, towards the end in the appendix, you're actually going to see these 3. Recurrent neural networks, LSTMs, and GRUs. These are actually used for time series data, which you hit at the beginning of the phase. If you want to do any sort of forecasting, these are the neural networks to look into. Actually very, very powerful in doing like seemingly random things like predicting like stock prices, even cryptos. These have been giving the best results so far. Autoencoders.
Can I ask?
Oh, yeah, absolutely.
So for RNN, LSTM, and GRU, could you use them to do multivariate forecasting?
Well, do you mean by taking in multiple inputs to predict one thing or predicting multiple things at once? Because you can do both.
Taking in multiple inputs to predict one output.
Yes. Yeah, you can do that. You can also predict multiple things simultaneously. I've actually never needed to do anything like that, but there is a functionality to do so. But yeah, it's sort of like, what is that, Ceramax, where you can give it exogenous variables. That is also a time series lab in the appendix, I believe. So yeah.
Okay.
Yeah, it's super cool. Another thing, for those of you who are interested in NLP, autoencoders are actually very, very similar to what is used to make word embeddings. So word embeddings is also in the appendix of phase 4. There's a lot of stuff in the appendix of phase 4, but autoencoders are actually what helps to create these word embeddings. Let's see, what else is in here? Convolutional networks, anything that is it this one? Yeah, convolutional networks, that is what you'll hit when you get to images, probably the next study group or within the next 2 study groups. That's something that you're going to cover. Other cool things, support vector machine. If you use the kernel trick with certain kernels, it can be interpreted as a neural network. And then also GANs. GANs are really cool. anything about like deep fake technology, that's actually through again. And it's really cool because you kind of have, it's called a generative adversarial network because adversaries, they're kind of like working against each other. You have two neural networks, one that's creating random things, the other one that's telling it whether what it's creating is good enough or not. And that's how it trains itself. So deep fake technology, that's again, but we're not going to hit GANs. It's not part of our scope. Not exactly data science either, but super cool to know that it's also a neural network. So yeah, neural networks, a lot of different forms of it. You can pretty much build any of these using the Keras library, but the main ones that we're going to use for data science processes like regression and classification, you're going to hit those in the next couple of study groups. All right. So kind of funny. One thing we're going to talk about the pros and cons of neural networks in a sec. But neural networks just generally have much stronger predictive power in comparison to all of the other models that you hit, like at the start of the last phase. You're in phase 4 now. Yeah, so last phase. Neural networks can pretty much do the same things as all the other models can. You can do a regression neural network, you can do a classification one, and you usually have much better performance overall. It does have its shortcomings, which we'll get to in a little bit. So some main applications, and let me zoom in so it's not tiny. Some main applications, you can use neural networks to do clustering. I know clustering was like one of the first few topics of this phase with neural networks, and I'll show you all, I'll like mention it real quick how you could do clustering with neural networks. You can do pattern recognition. Actually, that's very similar to when you do image classification. With a neural network, you can actually train a network to recognize things like textures, colors, edges in a photo to do like image classification or object detection. Image recognition, that's what I just mentioned as well. RNN, time series forecasting, or any sort of forecasting into the future. And what I was saying earlier with GANs, audio, video, image generation. So these are all applications of neural networks. So some limitations, because so far we've only said all the good things about neural networks. It is very, very computationally expensive. I actually currently have students working on the phase 4 project, and they are taking doing like a neural network version of grid search that those are running for like 12 hours. So neural networks can be very, very computationally expensive. Be careful of how many parameters you decide to tune with, because I just had a student who set up a grid search and has been running for like 4 out of 12 hours. What's really nice is they actually show you sort of like a progress bar. I'll link those libraries out to you later. But yeah, very, very computationally expensive, and we'll kind of explore why that is. Also, great for prediction, bad for inference. Because neural networks are so complex, we lose the power to infer from it. So things like our regression or our decision trees even, we can kind of do some sort of coefficient analysis, or we can do feature importances to learn from our models what the data is all about. Because neural networks are so complex and there are a lot of parameters involved, you actually lose the ability to interpret your model with respect to your data. That's a huge downside. All right, so first thing we're going to get into, the first technical thing we're going to get into is a perceptron. And a perceptron, in terms of its structure, is actually very similar to something that we've already seen before, which is logistic regression. And we're just going to kind of look at logistic regression from a slightly different angle to describe how a perceptron works. And remember that a perceptron is a building block for a neural network, and we'll talk about that scaling up in a little bit. So this is a diagram to get used to if you really want to get into neural networks. So you're going to get used to seeing all of these like circles pointing at places. The first layer of nodes are going to always be your inputs, and the number of nodes actually refers to the number of features that you have. So let's just say here we have M features in our data set. So this actually is for one single row of data. We have, let's just say this is 3 features. Each input is a different feature. Now, if you remember in logistic regression, you end up with coefficients that you multiply your feature by for your logistic regression equation. So what you have here is you have your input feature, multiply it by some weight, and you're summing it together. Actually, you don't even have to think about this as logistic regression. Linear regression works the same way as well. So you're summing together the input value and some weight that is going to be trained, sum it together, add an intercept term, but in neural networks terms, we call it a bias. So we're adding an intercept, pass it through an activation function, and then you get your output. So this activation function, this can actually look very different in different neural networks, but you can think about it in the logistic regression sense, you know how you have a sigmoid output that forces all of your output values to be between 0 and 1. That's an example of an activation function. So that transformation from linear to logistic, that's actually a possible activation function you can get, forces your values between 0 and 1, and that leads to your output. Now, depending on what your neural network task is, you can have different activation functions, but we'll focus on classification for now. This last activation function, think of it as you can actually have exactly a sigmoid activation function, force your values between 0 and 1, round it up or down to do your binary classification. So just to recap, the weights are determined by gradient descent, and we'll get into that process later on, though not very in depth. I have a good series of videos that I'll send out after this as well. The bias term here is our logistic regression intercept term, and the activation function is the sigmoid function that forces output values between 0 and 1, and the output is our classification result. So simplistically, we're just taking the dot product or the multiples or the element-wise product between inputs and weights, adding them together, adding an intercept, forcing values between 0 and 1, and that's our output. The hard part is what these weights are for a single perceptron. So we'll get into more of this and how a neural network learns, but pretty much every node in a neural network works this way. All right, so the perceptron algorithm is really about learning the weights for inputs in order to draw some linear decision boundary that allows us to discriminate between two linearly separable classes. So if you think about logistic regression, there was all this talk about having a linear relationship between your target and the log odds? So that's kind of what's connected to this linear decision boundary. Most of the models that we talk about have fairly simple boundaries. Of course, when we get to like max depth of a tree, that gets more and more complicated, but they're mostly made up of an amalgamation of linear boundaries. So what a perceptron will do, actually we talked about this already, takes in inputs, sums them up with weights, adds bias, applies activation function to get to your output. You can also have different activation functions. Again, as I mentioned before, depending on what your neural network task is, you can have a different activation function to give you different outputs. And then many perceptrons put together, you create a neural network. So this is an example of just a very simple perceptron output. Actually, if you're just running a logistic regression, functionally, it is a perceptron, but no one refers to logistic regression as a perceptron. All right, so, oh, question?
Yeah, could I just ask, why would you want to change up the activation function?
Yeah, so you could use a perceptron like this to do something like regression, for example. So let's just say we want to do regression. Instead, we don't have to force our values between 0 and 1. And this activation function is literally the function that forces the value between 0 and 1. So one possible activation is actually do like y equals to x. And that's pretty much a linear activation function for a regression. If you want to do a regression, you can actually set a linear activation function, and your regression result will just be the sum of all of these parts. So it's really dependent on your task. And actually, in some of my other notebooks, you won't get to this today, but if you want to check out my other notebooks, I'll actually point out, I'll give you all like a bullet point of where to find everything in that repo I sent out. There is actually a bunch of recommendations for if you're doing this task, use this function. If you're doing this task, use this function. Sweet. Anything else?
Is that something that we would iterate through? Like, is the activation function like something we would grid search for our model?
So you actually can. You can definitely grid search an activation function. Typically, though, the activation function that comes right before your output, you have fewer choices. Because, for example, if you are purely doing binary classification, you don't have many options for activation functions because you just have to choose one that forces values to be between 0 and 1. But we'll see with multi-layer perceptrons, there are going to be a bunch of activation functions in a bigger neural network, and I'll sort of point out where you could tune them. Neat. Awesome. All right, so next to level up, multi-layer perceptrons. Because perceptrons, based on this diagram over here, we have linear decision boundaries. A little bit too simple, let's go deeper. And that's truly the strength of a neural network. So it is possible with a neural network to get really, really complex with our decision boundaries, such that it can look something like this. And in terms of diagram, what that looks like is instead of having this diagram over here, where you just have a single node, of course, all your inputs are going into here, you have a single node at a bias, multi-layer perceptrons will look like this. And so in this example, we have 3 inputs. Each of these inputs are going into 4 different nodes. Now, each node that is within a hidden layer, each of these is a perceptron. So each of these nodes in the hidden layer have their own different set of weights for each input and their own unique biases that they're going to add for each input. Then what you're going to do is you're going to aggregate all of these node results. Again, put it through some activation function and then get your output. It is this aggregation from different nodes that allows you to get non-linear or just more complex decision boundaries. So yeah, each node in the hidden layer works like a single perceptron where they have their own unique weights and biases to every row's inputs. And then each node is going to transform the inputs and pass that through an activation function. And then the outputs are same aggregated to form a final output. All right, so each of these is working as a perceptron. That's important to remember. And then it's really the aggregation step that allows this decision boundary that looks as complicated as this or even more to occur. All right, so I'm just going to name some activation functions at this point. Sigmoid, which is literally the one for logistic regression. The one that we're going to see in a little bit is called ReLU. ReLU is actually the one that's most commonly used. And I'll talk about why that is used in hidden layers, and I'll talk about where that goes in. I think it'll make more sense when we look at implementation, but these are a bunch of different activation functions. The most commonly one that is used, as long as it's not the output layer, and what layers mean, we'll see in a little bit. You can use ReLU because that is typically, it's been shown to perform the best. And then yeah, for output layer, if you have a multi-class problem, you would use the softmax activation function, and you would use the sigmoid function if you have a binary classification problem. We're going to see this, and I want to do the implementation at the very end, but any questions, curiosities at this point? Okay, so let's talk about backpropagation. Backpropagation is very, very mathematically complex. If anyone has heard of StatQuest on YouTube, that's the series of videos I'm going to send out. They have a 5-part series just on backpropagation because it is very, very complex. So I'm going to send that out to you all later. But very, very briefly, why it's called backpropagation and overall conceptually what it is the gradient descent procedure of neural networks. So in gradient descent, you know, let's just talk about it in the sense of a linear regression. You start with some awful best fit line, and then slowly, you're going to adjust the parameters such that your line fits your data best. For backpropagation, why it's not just called gradient descent is because it's a little bit more complicated than that. You are having nodes that feed into other nodes that feed into other nodes. Perceptrons feeding into perceptrons feeding into perceptrons. So because of that, it has to kind of decide how do I deal with this error that can have different values at different parts of my network. So that's where backpropagation starts. The idea of backpropagation is basically it propagates these error terms backwards. So imagine you have a neural network with, let's say, 100 nodes at this point. At this point, it doesn't matter where the nodes are and how they're structured. If you have a row of data and you feed it through all 100 nodes, again, the order of those nodes don't matter, you have some error value at the end. Let's say in a regression problem, you feed your training data point through the neural network and you have like an error of, I don't know, let's say housing data. So you have an error of like $50,000. That's the error that you have at the very end of the node. Backpropagation looks to correct your error backwards through the neural network. So it's going to look, okay, at your second last layer, what was the error? What can we make better? And then it propagates it backwards again. And so it's sort of improving your network, starting from the last layer, going back to the first layer. So that's where the term backpropagation comes about. But essentially what is happening is just gradient descent, just in that order. Here, something to note is backpropagation is the process of picking the optimal weights for any forward feeding neural network. So forward feeding neural network implies that there are networks that are not forward feeding. For this course, we're only going to be talking about forward feeding neural networks because we have our data just going one way through the network. If we're pushing the boundaries of that, if we think about recurrent neural networks, we're not going to get into that. It's also in the appendix of your material. But to contrast forward feeding neural network, in a recurrent neural network, the reason why it's recurrent is because it's taking in new data sequentially. So let's just say your test data set has 30 points into the future. When you're making the prediction for day one, it's going to receive the actual data for day one and then use that error to make the day two prediction. So because of that, the direction in which your data flows through the network is not fully forward feeding. And so therefore, that's just to contrast forward feeding neural networks. If we actually take a look back at this, if we look at GANs are actually not forward feeding neural networks. They actually both go inwards and then outwards again. So just different ways of how neural networks can work. For now, if that didn't make any sense, not to worry at all. Okay. Any questions now? We're going to get a little bit more technical. All right. Oh, sorry, I haven't. In the chat. Will we still cover neural networks for time series? It is in the appendix, and I do have a little bit of material on that. I'm not sure whether your instructor will go through it or not, but there is material on it in the appendix. And it's in the repo that I shared out earlier, which I'll send you all like a bullet point list of where you can find each thing. All right. Okay, so how's this gradient descent done in terms of when you have a lot of data? How is that handled? So neural networks are usually implemented at scale with a lot of data. Therefore, optimizing for speed becomes a big concern. I've actually already seen, or I've personally worked with companies that have so much data that that you actually have to queue up training your model because they only have X amount of server space. If you want to train a model on like millions and millions of data points, you need to actually reserve some server space to make sure that you don't, use up all the allowance on their AWS server or something like that. So it actually does end up being a concern when you're working with very, very large data sets. So gradient descent can take a very long time to run if we're using a single training example every time to update the weights and biases. So imagine if I have a data set of 1 million rows, and with every single data point that goes through my neural network, I try and update the weights. That means this update process is going to happen 1 million times. That can be very, very computationally expensive. So therefore, to kind of subdivide our data sets, we have batches and epochs. So batches is smaller than epochs. So first, batches. So in batch gradient descent, you can actually define a batch size. And that's something that I think we'll see, but you get to define at some point a batch size. In a data set of 1 million data points, maybe I say I want my batch size to be 1,000. So that means we're going to pass all the examples through all the training examples through the forward propagation stage before using back propagation to compute weights and biases. What that means is, if I set a batch size of 1,000, that means I have 1,000 batches in 1 million rows of data. My network is only going to update every 1,000 data points. So it's a little bit more efficient that way, and it's going to update it based on an aggregation of the 1,000 data points per batch. So on a higher level than that, or at a bigger level than that, you also have epochs. So if you think about it, if you have this very, very complex neural network, this very first data point that you feed through your network, sure, it will learn a little bit from that very first data point. However, when you've reached the millionth data point, the information that was learned from the first data point might not be retained the same way, if that makes sense, right? If you think about what we talked about in phase 1, do you remember that as, I don't know, as clearly as the stuff that we talked about yesterday? So kind of that logic. So because of that, what you can do is you can actually run your neural network for a certain number of epochs, which basically is the number of times your neural network will see a single data point. And we'll sort of see that in action later as well. On top of that, there are different ways that a neural network can do gradient descent. You'll see this in the optimizers as well, which we'll also, I'll point all of these little things out when we do the implementation in a bit. So first, you can do stochastic gradient descent, which is updated after every observation in the training set. You can do it by batches, like what I was talking about before. When you have batches, it's only going to update the weight after all observations have been trained. And then you have mini batch gradient descent, which is kind of like an in-between. If you set a batch number, it's going to update it after each batch. So I actually misspoke earlier. Batch gradient descent will only update the weight after an entire epoch is done. If that makes sense. Cool. All right, so random initialization, something that if you think about, if you feed the same data through 4 different perceptrons, why would the 4 perceptrons end up being different? So in order to stop that from happening, the initialized weights and biases, the weights will be random values and the biases will be initialized to be 0. And that just stops each perceptron from optimizing the exact same way. Because what's the point of having 4 logistic regressions that will give you the same result? That will still result in the same linear boundary, so it kind of defeats the purpose. So therefore, we initialize the weights of our nodes to be random values and biases to all be 0. We do not initialize weights to be 0 because all weights will end up being the same. And also, this is actually something that is done automatically for you when you use Keras. You don't want to have very large initial weights because that'll saturate the value of the activation function, causing gradient of the activation function to be hard. Is just think about, you can think of that as setting very, very awful initial values that just has your network taking a long time to optimize. Cool. That was a lot of really technical stuff. I also want to mention real quick that deep learning and neural networks, that's like one entire college course. So the fact that we're doing this in like 3 hours of study groups is a lot of material crammed into one. So yeah, it's completely fine to at this point have a very just high level conceptual understanding of what's happening. Cool. Any questions before we get into implementation? All right. So I want to share with you all Google Collab. So Google Collab is really cool. It's basically Google's version of a Jupyter notebook that is built on their servers, is built on the cloud. A couple things that is pretty neat about them is you can actually connect it to different runtimes. So what that means is if you view, oops, not this one, I want to go over here. You can actually use their GPU or a TPU if you want to run your data faster or more parallel. So that's really, really cool. Also, what's neat is if you want to access data files or your own CSVs or images or whatever on Google Colab, all you have to do is upload your data onto your Google Drive. So this is unfortunately or fortunately connected to your Google account. So this can access your Google Drive. And all you have to do is just mount your Google Colab onto your Google, or mount your drive onto your Google Colab. And for the code, it's really just these 2 lines. I'm not going to run this right now because it takes there are a couple authentication steps. What'll happen, they'll just have you enter your Google password and it'll be able to access your drive from there. But other than that, this is pretty much a Jupyter notebook. You have like code cells and text cells. They don't call it markdown cells, but they are markdown cells. But yeah, you add code cells, add text cells. The downside is these shortcuts are slightly different from Jupyter Notebook. So I will say that even I'm not very comfortable using everything really quickly on Google Colab, but functionally does the exact same thing. All right, so to introduce neural networks, what we're going to use is Keras. So Keras is actually built on top of TensorFlow. In Python, there are 2 libraries that are both most well known for building neural networks. One is TensorFlow and one is PyTorch. PyTorch, I think, is built by Facebook. I don't want to say. PyTorch is built by a big company. TensorFlow is built by Google. And Keras is built on top of TensorFlow. It's sort of like how Seaborn is built on top of Matplotlib. You know how Seaborn makes Matplotlib a little bit easier to use. Keras is what makes TensorFlow a little bit easier to use. So we basically have different models, different kinds of layers, all these other things that I'll explain in a little bit. But Keras is the main thing that you use to construct neural networks. We're going to also use our typical pandas, NumPy, and scikit-learn for train test split. The data set I'm going to use is a very, very simplistic data set so that our neural network doesn't take a very long time to run. The Pima Indians data set that only has 768 rows. After we do the chain test split, we only have 500 rows in our training data. So this neural network is going to run really, really quickly, but just know that it scales up very fast. Yeah, and as you saw, it's pretty much shift enter to run the cells, exactly the same as the Jupyter notebook. All right. So steps to build your own neural network. Let's go back to here. So first, you have to think about the architecture. How many layers do you want? How many nodes do you want in each hidden layer? And what kind of activation functions do you want to use? So let's keep these in mind as we look at this neural network over here. So what you do, same as scikit-learn or similar to scikit-learn, you start by instantiating a model. So within Keras, they actually have a whole class of models known as sequential models that you can actually customize. What any forward-feeding model will be a sequential model. So here I'm just instantiating model to be sequential. From here, all you're doing is you're just adding the layers that you want. Now, the plainest layers that you can get, the most vanilla layers, are dense layers. So here we have a dense layer with 12 nodes. So what this means is you can think of this as there are just 12 perceptrons in this hidden layer. I'm also adding a second hidden layer with 12 nodes as well. I'll talk about these activation functions in a little bit. And then I have an output layer. And as you can see here, the output layer, the activation function is a sigmoid function because what we want to do is we want to do classification. So that's why this activation function is sigmoid. And then we only have one node because we only need one output. So back to talk about these hidden layers. The input dimensions, as I mentioned, that's actually important to specify for your neural network because it needs to know how many things to expect. The input dimension here is 8 because I have 8 features. My X train has 8 features. So however many features you have, that's your input dimension. Next, for activation functions. So between each hidden layer, you just have to have n activation functions so that it can translate the output of one layer to the next. Is there a reason why we choose 12 nodes? No, it's kind of arbitrary actually. The more nodes you have, the more granular granular your decision boundary will be. The more nodes you have also, the higher tendency you have to overfit. So pros and cons. All right, so that's the model building step, just by doing the instantiation of the sequential model and these 3 layers, I've built my model. However, in neural networks, you also have to compile your model. And there are several things to talk about when it comes to compiling. If you see here, there are things that you can specify. You can specify the cost function, which is basically, the cost function for how optimization works. Learning rate is something you can specify there, the kind of optimizer you want to use, and what metrics you want your neural network to keep track of. So as you can see here in model.compile, I'm defining this loss function. In loss function, there's actually a bunch of loss functions over here. If you want to take a look, there's so many different loss functions that you can pick and choose depending on what your problem is. Typically for classification, binary cross entropy. If you remember, entropy is pretty much like what you have for decision trees, the purity of each leaf. That's binary cross, very similar to binary cross entropy. The optimizer here I'm using is Atom. It's basically the path in which it chooses to get better. So whatever optimizer you choose to use, if you let them run for long enough, they eventually all converge to very similar results. But Atom for now has shown to be a better optimizer. And metrics, you can pretty much tell it what metrics you want it to keep track of. For now, just accuracy. So let me run this. And this step is basically building and compiling my model. So I'm going to take this one. All right, cool. And what we can see here is a summary of our model. So model.summary shows us that we have 3 dense layers, 2 input layer, 1 hidden layer, and 1 output layer. Now already here for this 8 feature 500 row data set, I have 277 parameters that are being trained. So you can imagine how this really starts to scale up. Now, again, I said 12 was kind of arbitrary. If I were to increase this to like 20, and really any number works, If I increase this to 20, you can see that my parameters go up to 445. So the number of parameters that are being trained are so much more, because if this was just a regular logistic regression, there would only be what, 8 weights and 1 intercept term to gradient descent on. But here there's just so many more, which is why you get those complex predictions. Cool. Now, to fit the neural network is actually the same. It's a dot fit. You're just giving it several more things. So first, your X train, Y train, that's state of scikit-learn. Number of epochs, as I mentioned, the number of times that your neural network will see your entire data set. So the number of epochs is 300. Verbose equal to 2 is basically what allows you to see this output, which I'll walk through in a little bit as well. Batch size of 100. So I talked about epochs and batches. Batch size of 100 mean it's going to look at 100 data points at a time. I'll talk about that later again. And validation data, we can tell it to look at X test and Y test to do the testing for us. So when I run this cell, it's going to look kind of intense, but it's a bit of a slow start. But there we go. Our neural network is training. It's training. I set it to run 300 epochs, but it's only 500 for the data, so it doesn't take too long. So it should finish in a little bit. Some numbers to note over here. At each epoch, it actually gives you your training and test metrics. It gives you your train and test accuracy numbers, as well as your loss. At this stage, loss is kind of just an arbitrary number for binary cross entropy. So it's kind of just a relative number. Also, other things to note, you can see that each new line is a different epoch. 6 out of 6 over here is basically the number of batches that you have. Because we set our batch size to be 100 and our training data has 514 rows, it's basically looking at 5 batches of 100, 1 batch of 14. So that's why it's 6 out of 6 over here. If you had a huge data set and like maybe a larger batch size, you'll actually see this slowly start to populate. So those are the important numbers to note. Also, something that you will see is that I have saved the fit step to history, which is not typical for scikit-learn, but it is useful for neural networks because we can actually see at each epoch how well it's doing. So in the next cell that I have over here, I have just plotting functions that is pulling out my loss and accuracy for my train and test. So if I run this, you can see that the loss gets better and better because that's how the gradient descent is being done. And if I look at my overall accuracy, yes, it is very jagged, but that's also because I only have like 100 data points in my test set. But you can see that it starts off not so great and very, very unstable, and it starts to plateau off. And so we have an overall train test accuracy of roughly 70%, which I don't know how this data set does on a regular machine learning model, but pretty good. I see a question. Are epochs and batch sizes up to us to manage training time? Yes, they're kind of up to you to decide. There isn't really a guideline or like threshold of like how many you want. Some people actually prefer to not use any batches because they want their neural network to truly update at every single data point. But yeah, to manage training time, larger batches is a little bit more efficient. Cool. So that is your first neural network. Any questions at this point while I think if I'm missing out anything?
I just had a quick question. How long would that take you just using normal Python Jupyter Notebook?
Not much longer. For this data set, not much longer. I think, well, it also kind of depends on your own computer. So I know that I have, this is the 2019 MacBook Pro. And I know it's like the highest one from Flannery School, runs about the same speed as this does. The downside is the MacBooks on your local machine, you actually run out of memory more than computational power, because if it's computational power, it'll just take longer to run. But if it runs out of memory, you'll see your kernel die. And that's something that you can actually manage over here. You can see how much RAM is being used. Right now, not much RAM is being used over here, but if you're storing a lot of weights in memory while you're training your network, that's when you want to switch over to Collab. Cool. Anything else? All right. Now, I didn't talk about making predictions, but basically to make predictions, you can do model.predict, and you just feed it in your X test, and you have your array of predictions over there. And I believe this just has to round up to 0 or 1, and you're all good there. Cool.
Could
All
we
right. Go ahead.
could we go over the graph again really quickly?
Oh, yeah.
Sorry, just so I can interpret it properly. Or so the y-axis is accuracy, but the x-axis is that
sorry, I should have mentioned the x-axis is the number of epochs. So basically, this is at the start of training, and this is at the end of training. So these numbers correspond to the accuracy numbers that you're seeing here.
Does that mean that, like, say, we should reduce the epochs to increase accuracy?
Reducing the epochs to increase accuracy, I'm not sure about that. I would say what you might end up seeing for a lot of neural networks. So you see how I've like train and test accuracy here. What's pretty common to see, and I'm just going to draw some like pretend lines for now. What's pretty common to see is your training accuracy, and I'm just drawing a red line over here. What's common to see is your training accuracy is going to keep getting better. As your neural network keeps learning things about your training data, your training accuracy is always going to improve. At some point, it's going to overlearn, and then you're going to see your testing accuracy. At some point, okay, over here is looking good, but at some point when it starts to overfit, your test accuracy will start to go down. And if you see that happening, and that's kind of why it's important to have this graph for neural networks. Thanks for bringing this up. I completely missed that part out. It's important to look at this graph because at some point you want to kind of control the number of epochs to some extent. So let's just say, okay, over here, I have like maybe the optimal number of epochs because this is before it starts to get worse. So I can say, all right, for my next model, I'm just going to stop it at 250 epochs. Something else that you can think of, actually just looking at this output over here, there isn't much marginal improvement after like 150 epochs, right? Like the overall, the training accuracy does tend to get a little bit better, but your test accuracy kind of plateaus out. Of course, not many data points, so it's very up and down. But because of that, to save on the computational power, you might say, all right, well, since it's not improving much after 170, I'll stop at 170 epochs.
Gotcha.
Yeah, all good. Any other questions? All right, well, I'm going to compile a bunch of resources and send it to your Slack channel in bullet point form. I'll show you all what's in, I'll like mention what's in each notebook that you'll see on my repo over there. And at any time, if y'all have any questions about not just neural networks, but any other product curriculum while Joel is out, feel free to let me know. I'll be on Slack as well. Cool. Oh, also, I know y'all are a part-time cohort, but actually tomorrow my full-time cohort is doing their phase 4 project presentations. So there will be a few presentations going on. I'll send out the Zoom link for that in case y'all are interested. I'll add it to your cohort calendar as well. Because I realize that y'all are like right around the same part of the curriculum. Cool. All right. Well, feel free to reach out to me if you need anything. But it was so nice meeting all of you. I'll put this recording up and send it out to Slack as well. And yeah, hopefully I'll see you all soon. Have a good night, everybody.
Thank you.
Bye.